Hi, my name is David. Today, I endeavor to teach improper integrals, as discussed in section 7.8 of the textbook. At specified times, you will be asked to pause the video to work out an example. For this, you'll need a pen or pencil and a printout of the provided note sheet. Let's get started. From previous chapters, we should recall the limit definition of the integral, or at least that it included a Riemann sum. Riemann sums take a finite region of the domain and range of the integral and partition that region into a finite number of rectangles, each with a finite width, representing a piece of the domain, and a finite height, representing the function value at a point. The definite integral from a to b, where a and b are in the domain of a function, therefore, is just the limit of the Riemann sum from a to b as the width of the rectangle scrunches down to 0. It's an infinity of essentially finite objects. Improper integrals deal with situations in which the traditional definition of definite integrals fails, such as when the domain of the region is infinite. In that case, we can't partition that domain into a finite number of finite width rectangles. It turns out that taking the integral of a function from, say, 1 to infinity can be useful in many cases, such as computing radioactive decay. But how could we do it? For a minute here, think about how you might do that, then write a sentence or two. If you need a hint, press play, but for now, please pause the video. Hint: think of limits. In calculus, the standard way in which we deal with situations involving infinity is by using limits. By taking the limit of a finite function as the value that goes into it approaches infinity, we can solve our improper integrals dilemma. Thus, we have the integral of f of x dx from a to infinity equals the limit as t approaches infinity of the integral from a to t of f of x dx, assuming that limit exists. This is an interesting conceptual leap, because we're essentially taking a limit of something that's already defined by a limit. Also, this method works equally well for integrals from negative infinity to a constant. For that, it's just the limit as t approaches negative infinity of the integral from t to a of f of x dx. We will refer to integrals of this type as type 1a. Please write down the box formula underneath your sentence. Pause the video here. Now, let's try an example problem. Evaluate the integral from 1 to infinity of 1 over x squared dx. Pause the video here. Did you get something like this? Here, I took the limit as t approached infinity of the integral from 1 to t of 1 over x squared dx. I didn't worry about the limit at the beginning. I calculated the definite integral, which equals negative 1 over x, evaluated at t and 1, thus getting a final answer of 1 minus 1 over t. Then I calculated the limit, as t approached infinity, of what I got from the integral. As t approaches infinity, 1 over t approaches 0, so I just end up with 1. Let's try an example together. This one does not need to be in your notes. We will calculate something that seems similar, the integral from 1 to infinity of 1 over the square root of x dx. First, we convert it into the limit of the integral from 1 to t. Then, we compute the integral, getting 2 root x, evaluated at t and 1. So, we end up with the limit as t approaches infinity of 2 root t minus 2. This limit approaches positive infinity, which means that the original integral increases without bound. If an improper integral does not give a finite real value, we can say that it is divergent. Conversely, as in the first problem, improper integrals that do give a finite real value are said to be convergent. Let's take a second to review what we've just learned. Improper integrals refers to integrals taken over some sort of infinity. For an integral of f of x taken from a to infinity, we can just take the limit as t approaches infinity of the integral from a to t. If the limit exists, the integral is convergent, but if the limit does not exist, then the function is divergent. Please pause the video now to copy this into your notes. There's another case involving an infinite domain that we need to go over. We'll call it a type 1b integral, when we have the integral of a function from negative infinity to positive infinity, or vice versa. If it goes from positive infinity to negative infinity, you'll probably want to reverse it. But don't forget to negate f of x if you do this. To solve a type 1b integral, break it into two integrals. One from negative infinity to a as shown, the other from a to positive infinity. In this class, we can basically always use 0 for our a value. Then, calculate the limit of each, just as before. Each integral must converge for the total integral to be convergent. Pause the video now. There's one issue with this method, though. Let's look at the graph of x cubed, from negative infinity to positive infinity. See if you can figure out what that integral becomes. Pause the video now. Hint: since it's an odd function, it would be intuitive if the integral were equal to 0. That's not it. To solve, we break the integral of x cubed from negative infinity to positive infinity up into the limits of these two integrals. Computing the integrals, we get negative t to the fourth over 4 and positive t to the fourth over 4. These limits approach negative and positive infinity. If this is the case, each partial integral is divergent, which means the whole thing is divergent. I repeat, if one or more of the partial integrals is divergent, then the whole thing is divergent. Similarly, if any of the limits does not exist, the entire integral is divergent. So far in this video, we've only looked at infinite domains. It turns out that definite integrals must be taken differently if the range is infinite. For example, if the graph contains a vertical asymptote. This actually makes perfect sense. If we consider a Riemann sum that involves an unbounded function, in this case a vertical asymptote, we realize that it would be impossible to fully account for the asymptote using the traditional rectangles. Either we'd end up with one rectangle of infinite height, or some rectangles of finite height that ignore the area under the asymptote. Unfortunately, we can't just throw up our hands and give up here. Sometimes, integrals of functions that involve asymptotes are actually convergent. These we shall call type 2a integrals. Let's take a look at the graph of 1 over the square root of x, from 0 to 1. If we think of the areas, the graph should actually be symmetrical about the line y equals x. Remember that the area of 1 over x squared from 1 to infinity that we calculated before? This integral should be similar to that one, giving us a total value of 2, one for the square right here, and one for the integral under the curve. Now, think of how you might go about this and write a short description in your notes, or see if you can solve the problem. Pause the video now. Once again, limits are the heroes of the day. To calculate this integral, we can just take the limit as t approaches 0 of the integral from t to 1 of 1 over the square root of x. That gives us 2 root x, evaluated at 1 and t, for 2 minus 2 root t. The limit of this as t approaches 0 is just 2. This approach works if the asymptote is at a boundary of integration, but if there's an asymptote in the middle, the integral must be broken up into two parts, separated at that asymptote. We shall call integrals of this type 2b integrals. As before, with the type 1b integrals whose domains stretch from negative infinity to positive infinity, a failure to break up the integral will yield an incorrect answer. From now on, you'll need to watch out for integrals, such as the integral from 0 to 2 of 1 over x minus 1 dx, that have an asymptote in the middle. See if you can solve this one. Pause the video now. Did you realize that the first limit doesn't exist, making the integral divergent? If not, try again and pause the video now. Let's take a look. As we might expect, we break that integral up into two parts. The first limit is the limit as t approaches 1 of the integral from 0 to t of 1 over x minus 1 dx. The second is the limit as t approaches 1 of the integral from t to 2 of 1 over x minus 1 dx. Calculating the first integral, we get the limit as t approaches 1 of the natural log of the absolute value of x minus 1, evaluated to t and 0. The natural log of 0 doesn't exist, making the entire integral divergent. Note once again that if the limits involved in calculating an improper integral, if one of the limits involved, I should say, in calculating an improper integral is divergent, then the whole integral is divergent. So there we go. I'm done making your life more difficult. Now, let's make it easier with the comparison test. The comparison test is relatively intuitive. If you have one convergent function g of x, and the absolute value of a function f of x is less than or equal to the absolute value of g of x, at least on the domain for which we're integrating, then f of x is also convergent, since its integral will be smaller than another finite integral. Watch out though, if f of x's absolute value is sometimes or always greater than g of x's, you cannot make a conclusion about whether or not it's convergent. As you might expect, the comparison test goes the opposite way for divergent functions. If you know that a of x is divergent, and that b of x's absolute value is greater than or equal to a of x's absolute value on the domain over which we integrate, you can say that b of x is divergent and call it a day. If, however, b of x's absolute value is sometimes greater, you cannot make a determination using the comparison test. Let's set up a flowchart for what to do with an improper integral based on what we've learned. You'll want to copy this into your notes. Let's start with the integral from a to b of f of x dx. First, if we can find a divergent function that is smaller than f of x on the closed interval ab, we're done. The function is divergent. Unfortunately, that won't generally be the case, so we should look at whether the function is convergent. If we can find a convergent function that's greater than f of x on the closed interval ab, we know that the function is convergent. If we're answering multiple choice questions, we can eliminate, quote, the function is divergent. Whether or not we can, we'll almost certainly need to move on to the next step now. Now we'll look at a and b. If one is an infinity and the other is a constant, at least for calculus BC, we know how to calculate it. Note that AP Calculus basically never combines multiple types of improper integrals in one. This is a type 1a improper integral. Let's say that b is positive infinity. We just take the limit as t approaches infinity of the integral from a to t of f of x. If, when looking at a and b, we find that both are some form of infinity, we're looking at a type 1b improper integral. If we have the integral from positive to negative infinity, we can just switch the signs on the infinities and negate the function inside if we want to. If, however, we have the integral from negative to positive infinity, then we can just break it up into two different limits. The limit as t approaches negative infinity of the integral from t to 0, and the limit as t approaches positive infinity from 0 to t. Since AP Calc BC doesn't combine different types of these improper integrals, using 0 as the middle point, I guess, will basically always work. If a and b are both constants, then we should check carefully. If f of x is defined at both a and b, and on the interval between them, we're golden. It's not an indefinite integral. If f of x is undefined at a or b, we have a type 2a integral and must use the limit. So let's say there's an asymptote at b. Our limit will be the limit as t approaches b of the integral from a to t of f of x dx. Not too bad. Let's look at our final case. If f of x has an asymptote, other discontinuities don't really matter as much. Somewhere between x equals a and x equals b, then we have to divide the integral up. This is a type 2b integral. So, if the asymptote is at x equals c, where c is between a and b, then we have the limit as t approaches c of the integral from a to t of f of x dx, plus the limit as t approaches c of the integral from t to b of f of x dx. One last note that you should all have at the bottom of the chart, maybe underlined or put in all caps or both. If any of the limits fails to exist, the entire integral diverges. Please finish copying the flowchart and pause the video if applicable. There you go. Chapter 7.8 in 15 minutes. This is a fairly difficult topic, so don't worry if you're not 100% sure you can do it. The AP exam doesn't really emphasize improper integrals, and the flowchart containing the 4 types is really the only thing you'll need to remember for this topic. So thank you for watching.